So we've talked a bit here and there about the analogy between the complex numbers and the operators on V, and I thought it would be good just to sort of take a moment to tack down kind of precisely the correspondence. So on the one side, we've got complex numbers, and we've got the operation of conjugation. And if you do it twice, you get back where you started from. And this conjugation respects all of the field operations that you have for the complex field. Meanwhile, if we look at an operator, then we can take its, on an inner product space that is, then we can take its adjoint. And we know that if you take the adjoint twice, you get back where you started from. And this operation of taking the adjoint also respects the algebraic operations that we have going on here. Then we have like special classes of complex numbers as defined by their properties with respect to conjugation. So for example, if we have that the conjugate equals the original number, then that tells us that we're in this special subclass of numbers that we call the reals. Similarly, if we have that t star is equal to t, then we're in this special subclass that we call the self-adjoints, and it follows that the spectrum of t is contained in the reals, and that's in fact if and only if. I guess both of these are if and only ifs. Then given a complex number, we can also look at the, and there's also the positive numbers. So there's this notion of positivity for real numbers, so numbers that fall in this special subclass. And we also have that certain self-adjoint operators, namely the ones with non-negative eigenvalues, are also positive as well. Then we can also talk about the real part of a complex number. And the way we find it is we take a number and we add it to its conjugate and divide by 2. And the imaginary part of a complex number is z minus z conjugate over 2i. Okay, and notice that both the real and imaginary parts here, these guys are both real numbers. Now, and that's part of the reason why we divide by the I right here, to make sure that these are both real numbers. So putting it back together, you have that z looks like real part of z plus I imaginary part of z. So both the real and imaginary part are real, despite the name imaginary. Similarly, we can also talk about the real part of t as being t plus t adjoint divided by 2, and the imaginary part of t as being t minus t adjoint divided by 2i. And in this case, we end up with two operators that are both self-adjoint. And you can see that if you add these together, t is going to be the real part of t plus I times the imaginary part of t. And okay, so continuing on, we can also talk about the polar decomposition, which is the main focus of 7.D. And so we can take a complex number and we can write it as e to the I theta times r. And so here, e to the I theta is going to be a number of magnitude 1, and r, which is the length or modulus of z, is going to be a non-negative number. Now the exponential part, by the way, if you haven't seen complex numbers, if you're not so familiar with complex numbers, then you should think of this guy here in terms of Euler's formula as being, cosine theta plus I sine theta. And then you can see that it's a unit number by, sorry, let me back up even further. Cosine theta, sine theta, in terms of the standard parameterization of the unit circle. So that shows you that it's a number on the unit circle, and you see that it's a number of modulus 1 algebraically by using Pythagoras' theorem. So cosine squared plus sine squared equals 1. Okay, the exponential is not quite so straightforward for the operator side, but we can do sort of a different thing. We can take z and rewrite it as a unit vector times a positive number. And then we can actually split that even more. So here we've got, there's our unit vector, and then if we square it and then take the square root, then it's the square root of z times z conjugate. And in fact, you can see that these correspond, right? Okay, so on the operator side then, we can take our operator t and we can write it as s times square root of t star t, where s is unitary, so it's a, and I forgot that part of the analogy. Okay, I'll add it in just a second. Where s is unitary and where square root of t star t is a positive operator. Yeah, okay, so I forgot. So there's the unitary. So we've got the ones with magnitude z is equal to 1, and these are the ones where z is equal to, z conjugate is equal to 1 over z. And on the operator side, we have the unitary operators. And these are the ones that satisfy the adjoint is equal to the inverse. Okay, all right, so I think that's basically all of the points of the analogy that we have talked about so far. And so just to clarify, in this chapter, if t is a positive operator, then we know that it has a unique positive square root. So we'll always use this symbol root t to be that unique positive square root of t. And so this is well defined by that theorem 736 that we did before.